we did the caudal graphs, right? This one we did that every caudal graphs are perfect, right? Okay. So next definition we have. So it is a transitive orientation. So we'll define what is a transitive orientation. So this is the definition. So a transitive orientation of a graph G is an orientation D such that whenever x and y such that whenever xy and yz are edges in D, so there is also an edge also there is an edge xz in G that is oriented from x to z in D. So if xy and yz are edges, that is in the orientation D, then xz edge is also there, that is oriented from x to D. So that is the definition, transitive orientation. So the transitive relation you remember, right? So that is something similar to that. So transitive relation is x is related to y, y is related to z, then x is related to z, right? So that is a transitive relation, right? So similar definition. Okay.
Yeah. That's mean X, Y, Y, Z, and it
Yes,
Z
yes.
is connected. So it is a loop is one.
Yes, you can say loop, but it is not in the same vertex, right? So it is a cycle, you can say. So x to y, y to
Circle,
z, that will
circle,
implies x to z.
circle.
Yes. So this is the definition of transitive orientation. So now a simple graph. A simple graph G is a comparability graph. Comparability graph if it has a transitive orientation. So yes, so this is the definition of comparability graph. Fine. Right. So an example is, let us see an example. So example is if G is a XY bigraph, then directing every edge from X to Y, that yields a transitive orientation. So
Bigraph.
that bigraph is bipartite, right? So bipartite graph with this partition.
Okay.
Yes. So directing every edge from X to Y yields a transitive orientation. So what is happening here is, so G is a bigraph. So this is the two partitions x and y. So some vertices are here, suppose, and some vertices are here. So any edges I have, so I give the direction from x to y. So this is the direction, right?
mm,
So if we have this direction, then automatically this it is vacuously true, right? Because what it so whenever xy is an edge and yz is an edge, right? But this condition will never come, right? Because suppose this is x and this is y, right?
H to
So
Y.
x to y, suppose, but from y there is no edge to the other direction, right? Because
Oh,
the edge is moving towards this. So by vacuously it is transitive, right?
transitive. S to Y.
Right.
Y to Z, we don't have Y to
No, no,
Z.
we don't have y to z, right? So that's why we don't have to satisfy this x to z condition also, right?
So we don't have S to Z.
Right.
So we cannot say transitive
No,
orient.
no, no. The thing is that they are saying whenever there is an edge x to y and y to z, right?
Yeah.
Then this edge must have, right? But this first condition itself it is not satisfying, right? Because only the edges are from x to y, like this, right?
Oh,
So
oh,
there is no edge from y to z. So it is
mm,
trivially true. So it is just true,
mm, mm,
right?
mm, mm. Phone imply phone.
Yes, tell.
Yeah, yeah. Oh,
Fine.
mm, yeah, yeah. Mm,
Right. So so this type of orientation. So they are asking for existence of an orientation, right? If there exists a transitive orientation. So the one orientation I have given. So hence, thus every bipartite graph is a comparability graph. Graph. That is fine. So now the next proposition is, so it says that comparability graphs, these are also perfect graphs. So perfect graphs definition you remember, right?
Rima is
Yes.
perfect.
So perfect graph we defined here, right? 1 minute. So yes. So a perfect graph, a graph is said to be perfect if the chromatic number is same as the click number for every induced
Mm,
subgraph.
mm, mm, mm,
Okay.
mm, 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 mm. Yeah,
Right.
yeah. Mm.
So let us see how to prove it. So the proof is, so every induced so since it is a transitive diagram, so every induced subgraph is also transitive, right? So every induced subgraph of a transitive diagram is transitive. So the class of compatibility graph, that is hereditary. So this is hereditary. Now we only need to show that the chromatic number is actually equals to the click number. So show that each comparability graph G is omega G colorable. So omega G is the click number. So if we can show that omega G is that G is omega G colorable, then we have that the chromatic number is omega G, right? Okay. So let us see. So let F be a transitive orientation of G. So note that F has no cycle, right? Because if we give a orientation, so suppose this is X, this is Y, and this is Z. So we have X to Z and Y to Z. By transitive orientation, it implies that from X to Z there is another edge, right? Direction, right? But this is cycle in the undirected case, but in directed case is not a cycle, right? Because if it has to be a cycle, I have to go like this, right? But this edge is coming here, so this is not a cycle, right? So yes, it has no cycle. So the coloring of G assigned to each vertex the number of, okay, so the coloring of G that assigns to each vertex V the number of vertices in the longest path of F ending at V is a proper coloring, right? Right. So what is happening is, so suppose I take the longest path. So for example, let us take five vertices. Suppose so, then I have from X to Y. Suppose an H is there. So this is the longest path. So I have given the orientation, right? So now X to Y and Y to Z is there. So this should be there, right? Now X to Y to Z is there. Z to V is there. So this edge will also be there, right? Now Z to V and V to U edge is there. So Z to U edge is there, right? This is there. Now if I consider these two things, so X to Z is there and Z to U is there, right? So this edge should also be there because it is transitive, right? So now, right. So now if I see one more edge should be there. Let me think. So X to, right. So for example, X to Y is there and Y to V is there. So X to V is also should be there. So like this, you can see that we can. So if I, for example, if I take these four vertices, so in fact you can see that that is a click, right? Because all the possible edges are there because it is transitive. Right. Similarly, if I take the whole thing, then it will be a K5, but with some directions, but that will be a click, right? So that's why if I take a proper coloring of this path, then I am done because each will get a unique color, right? Because of the adjacency, right? So that's why. So this will be a proper coloring. So by transitivity, the vertices of a path in F form a clique in G. So at most, so hence the chromatic number is less than equals to the clique number, because that is the largest size of the clique possible, right, in the graph.
Mm.
So it is so the chromatic number has to be equal to the omega of G, that is the clique number, and hence the graph is perfect,
Mm.
right?
It's okay. Mm.
Right. So the next one is, so we have found this is the chromatic polynomial, right? So G comma K. So this is the chromatic polynomial, right? Right.
Mm.
So now we have always seen that this K is a non-negative integer, right? It is greater than zero, or you can say yes, greater than equals to zero, right?
Mm.
Because K denotes the number of colors we are using to color the graph, right? Okay.
Mm.
So, but what happens is K, if K is negative, then graph theoretically does not make sense, right? Because what do we mean by
Mm.
negative number of colors, right?
Mm.
But actually, there is a sense. Actually, there is a meaning. So let us see what happens. So, what happens when K is a negative integer?
Mm.
So it is saying, so an acyclic orientation. So orientation means we are giving direction to the edges, right? So
Mm.
acyclic orientation is we are there is no cycle after we give the orientation to the edges. So an acyclic orientation of a graph is an orientation having no cycle. Right.
Mm. It's okay. Mm.
So actually, if I set k equals to 1, so setting k equals to -1 in this chromatic polynomial actually enables us to count the acyclic orientations of a G. Right. So this is a one observation. So there we'll see through an example what is happening. So up to this is clear.
Mm. Yeah. Clear about statement. Yeah. Yeah.
Yes. So let us see an example. So if I consider the C4, so this is my C4. So there are four edges, right? So how many possible orientations are there of C4?
Orientation.
So orientation means we are giving
Oh.
direction to the edges, right?
Mm.
So for each edge, I can give the this direction, or I can give the opposite direction, right?
Yeah. Yeah.
So
Yeah.
how many possible orientations we have?
Mm. 2/4.
No, four square, right? Each edge has
4. Two.
yes, yes, that is same 2/4, right? Right,
Mm.
that is correct. So each edges has two options. So it is 2/4, right?
mm,
There is 16 orientations are possible, right?
mm,
So okay, let me just, so among these orientations, so if I take these two special type of orientation, so then it is a cycle, right? Or
mm,
if I take the opposite counterclockwise, so if I take the counterclockwise, that is also a cycle, right? After giving orientation.
mm,
So other than that, all the remaining orientation is acyclic, right?
mm,
Right. So there are only two cyclic orientation of C4, and the remaining 16 minus 2 is 14 acyclic orientation, right? So now, if we remember the chromatic polynomial, so I'll just recall it. So this is given by k into k minus 1. This we did earlier. So this is the chromatic polynomial, right? Of cycle.
mm, mm,
So now, if we substitute, so suppose this is, if we substitute k equals to minus 1, then what happens? So this is equals to minus 1. Wait, how much is that?
mm. No, oh, 7 and minus 7. Oh,
Right?
yeah, yeah. Mm,
So it's minus 1 into minus 2 into 7, right?
mm,
So it is 14. So that is matching, right? So here also we got 14 acyclic orientations, and if I evaluate at minus 1 the chromatic polynomial, that is also give 14.
mm,
Okay. So that is what the this was saying, right? So if I put k equals to minus 1 in the chromatic polynomial, so this enables us to count the number of acyclic orientations in G.
mm, mm,
So the example is fine, right?
It's okay.
Okay. So okay. So actually, the next theorem gives a more generalized statement to this thing. It states that the value of the chromatic number or the chromatic polynomial at k equals to minus 1 is minus 1 to the power n times the number of acyclic orientations of G.
Mm,
Okay.
mm.
So n is the number of vertices. So it is minus 1 times the number of acyclic orientations of G.
Value is
Fine. The statement.
the value of
The chromatic polynomial at the k equals to minus 1. So if I evaluate the value,
time of number quick. What does it mean? N. What is N?
n is the number of vertices.
Number of it.
Yes, yes.
So it's just one or minus one.
No, no, no. Let me write down.
Time. Okay, time.
Right, right. So
Okay.
now it is minus 1 to the power n times the number of acyclic orientations.
Oh, so if the number is even, we have negative.
Mm,
N is 3, for example. We have minus 1.
yes, yes. Okay, that will let me explain. So the thing is, what is happening is, so the number of acyclic orientations let us denote by A of G. So A of G, okay, let me write down here. So the number of acyclic orientation is A of G, right? So it is
Mm.
saying the chromatic number of G evaluated at this K, it is evaluated at K equals to minus 1. So this is nothing but minus 1 to the power n times A of G, right? So
Mm.
when n is odd, so this will become minus 1, right?
Mm.
But this will also come negative. So that's why this term will always remain positive or greater than equals to 0. This term is always greater than equals to 0.
Become to zero. Uh,
This one is always greater than equals to 0. This is not negative. So
mm.
if n is even, then this will come positive and this will is also positive. And if n is odd, this is negative, this will also come negative.
Got it, got it.
Okay. That's why this adjustment is there.
So the chi should be negative.
Yes, so that will come negative when it is odd.
Mm.
So that let us see the proof, you will understand what is happening. So the proof is, so we'll use induction on the number of edges.
Mm.
The number of edges. So A of G is the number of acyclic orientation. That is fine. So when G has no edge, so it means it is isolated vertices. Then the number of acyclic orientations is one, right? That is, it is vacuous, right?
Mm.
And the chromatic polynomial, it is nothing but minus 1 to the power n, right?
Mm.
So the claim holds, right? So the claim is true, right? For when the number of edges is
That.
0.
Mm.
So this is our base case. Now we will prove that there is a relation between the number of acyclic orientations of G and A of G minus C plus A of G dot E. The deletion and contraction, there is a relation for E belongs to the H set. So if E belongs to the H set, then A of G is related like this. Right. So once we will prove that, but before that, let us see how
Mm.
this will help. So if this is done, so then we can apply the recurrence relation on A
Mm.
for the induction hypothesis, right? So if so, so then we apply the recurrence relation for A.
Mm.
Now we can express by induction hypothesis for A of G in terms of the chromatic polynomial, right?
Mm.
So now let us see how to do. So we know that it is the result is true for up to lesser number of edges.
Mm.
So A of G minus C, it has one edge less. So now using the induction hypothesis, that is, it is number of edges, number of vertices is fixed, right? Because we are only deleting the edge times the chromatic number of G minus C evaluated at minus 1. And when
Mm.
I contract the edges, number of vertices is reduced by 1. So it is minus 1 to the power n minus 1. The chromatic number of G dot E evaluated at minus 1. So up to this is clear, right?
Mm. 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 Yeah, yeah.
Right. Now if I take a minus 1 to the power n common, so if I take minus 1 to the power n common, then I have g minus c minus chromatic number of g dot e minus 1, right? But chromatic number recurrence, I know that this thing is nothing but the chromatic number of g evaluated at minus 1, right? This is the chromatic number recurrence relation, right? Fine. So this is done. But now only thing left to prove is that this recurrence relation actually holds. Right? So let us see how to prove that. Let me copy this one. So this is what you have to show. Now every acyclic orientation of G contains a acyclic orientation of G minus E, right? Right. So actually, what is this statement? You understood it. So every acyclic orientation of G, it contains an acyclic orientation of G minus E, right? So for example, suppose we are considering this cycle C4, and let us give a acyclic orientation. So right, so this is acyclic, right? This orientation is acyclic, right? So now suppose this is my edge E, and we are considering G minus E. Then I have this graph. So if I just copy the orientation, so this is also acyclic, right? G minus E, right? So this statement is clear, right? So every acyclic orientation of G contains a acyclic orientation of G minus E, right? Now, given a acyclic orientation of G minus B, so G minus E, let me write down D of G minus E. So we can extend that acyclic orientation to either 0 or 1 or 2 acyclic orientations of G. Right. So the thing is, what is happening is, so from here to here, so I can there is only one acyclic orientation, right? Because I delete this edge, whatever is left out, I keep it as a acyclic orientation of G minus E, right? But on the other hand, the thing is happening is, so from G minus C, if I want to go back to G, then I have a few choices, right? So what is happening is, so from here to here, this is one choice, that is fine. We have one more choice, right? So if I draw like this, so this part I keep as same, but now I give this direction. So this is also acyclic, right? So from here to here, so this is also an acyclic orientation of G, right? So any acyclic orientation of G minus E, it can extend to 0, 1 or 2. 0 means it can happen that it does not give any it does not arise to, it becomes a cyclic orientation for G. That can also happen, right?
Okay.
This fine.
Mm.
Accelerate by orienting. AG, right?
Mm.
Now, when D has no UV path, so UV, so this edge is between U and V. Suppose there is no UV path, we can choose V to U, and when D has no VU path, or yes, VU path, we can choose the other direction. So that's why it remains acyclic. So that's why we are doing that. U to V. So since D is acyclic, D cannot have both of them. Right?
GV bạn. Dạ. GV bạn.
So the two choices of E
VU bạn. GV bạn.
cannot be forbidden. Fine.
Dạ.
So hence we can at least extend the orientation from G minus E to the original graph in at least one way, right? So that is what you're saying. So every D extend in at least one way, and A of G equals A of G minus E plus the number of orientations that extend in both ways. Right? So what we did is we first observed that any cyclic acyclic orientation from G minus E, I can extend it either 0, 1 or 2 ways, right? But now we first show that 0 is not possible. At least 1 we can always do. That is, suppose this edge is missing, right? This is from U to V, right? So since the orientation is acyclic, both paths from U to V and V to U, that is not possible, right?
Yeah. It's
So we'll choose that path. That is, if U to V is there, we'll choose V to U. If V to U is there, I will choose U to V, right? So what I show is that every D we can extend at least in one way to G, acyclic orientation. Now, for some, it will happen that both ways I can extend it, right? A particular edge, you can extend in both ways, right? For example, here, so this edge is missing. This I can give any orientation. I can give this orientation or I can give this orientation. Both of them are acyclic, right? So that how can we count? We can just that or in the original graph, if I merge these two edges, that is the edge contraction. If I do so, then I have a triangle, right? So if I merge these two edges, then I have a triangle, right?
It's okay.
So that is how I am extending the remaining part. So So those which are extended in both ways are the acyclic orientations of G minus E with no UV path and no VU path. So they are exactly G dot E, A of G dot E of this, right? So hence we can say that A of G is nothing
Mm.
but A of G minus E plus A of G dot E. So the reconciliation is proved. Once the reconciliation proved, we have already shown by induction that the remaining result holds.
Yeah, yeah. We do induction and we assume and we prove the assume.
Right.
Mm.
Fine.
Mm. It's okay.
Right. So next what we have is
We can do here.
okay. Okay. Bye then.
Mm.